So in this video, we are going to talk about Venn diagrams, and then I forgot something in the earlier video, that is to talk about power sets. So what we want to do first is that we want to recall that we define something like an universal set, which is again a hypothetical set, and it supposedly contains everything, whatever object that you are interested in. For example, um, if you want to construct an universal set that contains humans, then you can just take the whole population of Earth, assuming humans only live on Earth, that is. So that would be a universal set. However, like every set that you work with will come from this universal set and stuff. And you can see that I have a diagram over here where you can see a rectangle, and then there are some circles that is labeled as A, B, and C, and I'll get to the explanation of what they are. So the idea of Venn diagram is that if we have some sets that we are working with, we just want to represent them visually with the help of diagrams, of course, so that we can just remotely try to visualize what is really going on. So I have used this rectangle to represent this universal set, and this picture itself is the Venn diagram, named after some guy named Venn, or mathematician. I shouldn't call him a guy, rather a mathematician, but whatever. That's really not none of our concerns right now. So what we want to understand is that how can we try to visualize the operations that we saw, union, intersections, and so on. So let's get into it. So the universal set is U, which is this whole rectangle. Like if you forget about A, B, and C, this whole rectangle is your universal set, or U. And then you have some other sets marked as a circles, set A, B, and C. And if you notice, this sets A, B, and C, they're coming from U. That is, it's like taking a portion out of U. So this A, B, and C, they're all subset of the universal set. And this is just a Venn diagram, an example of a Venn diagram. So whenever you have some sets and you can represent them with circles, rectangles, or whatever figure you want, you can call that a Venn diagram. Instead of a rectangle, I could take my universal set that looks like this, some arbitrary shape. And I could label set A as this, B as that, and C as this as well. And it's also fine. This is also a Venn diagram. But from what I know and I have seen so far, people usually go for this sort of figures because somehow it became a convention. But there is nothing wrong with this diagram as well. So whenever you have some sets, you can draw some pictures for each and every one of those sets, and those pictures will represent whatever you're doing algebraically, and those pictures I'll just call Venn diagrams. That's it. That's all about Venn diagrams. Now comes to the part, now let's go into the part where we want to talk about how we can see the operations on sets through Venn diagrams. So let's say you have two sets, sets A and B. And what are the stuffs that you can do? You can have a union of them. You can define an intersection, right? And finally, the set subtract thing that we defined in the last video. Set subtraction thing. So far, these are the stuffs that we did. Now there can be many more things, but since this is a pre-calculus record, so I'll not go deep into that. You can have Cartesian products, you can have a different type of products between elements of sets, but those are some advanced stuff, so I don't want to talk about them in this video. Maybe someday else. but that we won't need that. So these are the basic operations, and we'll need this three so far. So let's try to picture a union. So what happens in a union is that you have two sets, A and B, and let's say you have some elements of A, let's say 1, 2, 3, and let's say you have B as 2, 4, 6. If you compute their union, this is just 1, 2, 4, 6, 3. Now, if you are asked to do a Venn diagram of this thing, you can draw set A like this, let's say, and then you have set B, and you want to unite them. So what is the union? The union is a bigger set that contains all the elements of A along with the elements of B, right? So if this figure contains the elements of A and this figure contains the elements of B, union is just what? Doing gluing them together, right? That's what we are doing in here with the algebra. So you can just draw something like this. You know, think of it like um, cell union, I guess. I'm not sure. Like cell division, cell union. Maybe biologist people can picture it better, but I cannot. So I just imagine like they will just, you just glue them, that's it. And the figure will look something like this, A union B. If you want to do it formally, you have one circle and then there is the other circle, the meet somewhere in between. Oops. So your figure looks something like this, and so on. Usually people don't ask about, the Venn diagrams of the unions, but what they do ask about is to show the intersecting region between two sets, and we'll discuss that now. So this is all about union. This is how you can represent a union using Venn diagram. And obviously, if you want, you can always put an universal set over here. Doesn't really matter, to be honest. As long as you understand what you're doing, really doesn't matter. And then we want to define an intersection or show what intersection really means through Venn diagram. So again, if you have set A and set B and you wanna find the intersection in between them, let's say this is set A, set B. How do we find the intersection? Well, algebraically, let's say A is again 1, 2, 3, B is again 2, 4, 6. And if you try to compute the intersection, this is just 2. Now, one thing that I want to mention is that it's a remark. That is, you can, some people write it like this, like they introduce the null set, but some people don't. So it's really up to you, whatever notation that you're using. So if two sets have nothing in common, the result is a null set. And null set and no set is really empty. It will always contain a null set, but sometimes containing a null set is just equivalent of containing nothing. So yeah, it's a little bit confusing because by not containing anything, we usually think that that space is empty or something like that. However, if you think of it like this in a broader terms, let's say you are trying to count how much money do you have with yourself right now, and let's say you are a brokey like me. I have $0 on my pocket, so that means I have nothing. But then again, zero is still a measurement of how many dollars do you have in your pocket. So in that sense, when you try to do set theory, the null set is something that is equivalent to zero. So some people write it, some people don't. For us, I'll just not write it. I'll just assume it's there. Okay, so now we want to represent this thing through Venn diagram. So how do we do it? Well, we are finding the common element, right? So if I have set A and B and I want to find the intersection, it will look something like this. This is again A, this is B. Again, the shapes don't matter. You can deform these shapes if you want to. So if this is A and this is B, this common region that is shared, the overlapping region, this is called A intersection B. This is your intersection, okay? All right. And there is another remark, I'm not sure if I mentioned it in the other video, is that if two sets, let's say A and B, have no elements in common, the result of A intersection B will be the null set. So this is another remark. Like there's nothing in common, and null set is the symbol or the term that we use to signify that. All right, so now I want to come to the final topic of this video, is to show you people set subtraction using Venn diagrams. All right, so let's say I have a set A, and again, the other set is B. So I want to subtract B from A, and let's say again A is 1, 2, 3, B is 2, 4, 6, and if I do it algebraically, the things that we saw in the other video is that this is something like 1, 2, 3, subtract 2, 4, 6. The idea was to get rid of everything from B. At the same time, we seek if there are any common elements between A and B as well. If there is, we get rid of that as well. So here we have a 2 common in between these two sets. So the result would be just 1 and 3. Okay. Now, if you draw a Venn diagram like this, let's say this is A, this is B, how do you do this? A subtract B. It's very simple. You take A, right? This is A again. And what you do, you take B and put it on top of A, let's assume. Like, you are trying to overlap these two sets. And now you can see a new portion like this, right? Sorry, the dashed line came off a bit. It should be from here, like this. Now you want to take this guy off. That means this red portion, you just want to cut it off. You cut it off, what happens? The shape of A changes, right? Something like this. So if A was a cookie, and let's say B is, I don't know, the side with the vanilla cream or something, I guess. So it's like taking a bite out of that cookie, but only the portion with vanilla. So yeah, okay, I think I have a better example now in my mind. Yeah. So let's say A is a cookie that contains half chocolate, half vanilla, and you are somebody, for some reason, some weird reason, you like vanilla really very much. So your choice is some sort of a sector B or set B, and A is that cookie. Now you will only eat vanilla. So the way you can do it is to subtract that vanilla portion out of your cookie. And to do that, you need this bite. I know that was a really, really bad example of what set subtraction is, but I think that's the most practical example I can give you right now. Yeah. But if you have any better comments, better examples in mind, you can just comment it down in the video. So yeah, that's all about Venn diagrams. This is pre-calculus. So the main reason for discussing sets so that you can catch up when we talk about functions and use intervals and stuffs like that. Oh, and there's one thing I forgot to mention again. is I haven't talked about something called a power set. It's nothing special. I mean, for me, it's not. Maybe for somebody else it is. I don't know. So power set is something, let's say you have a set A, 1 and 2 and 3. Now you can have subsets of A, right? Subsets are what? Subsets are just smaller portion of A. Those are also sets. So what I can do, I can make new subsets. One subset can be one, just one. And I mentioned before, like null set is always there, no matter what set you write. So null set is there. Then you can form another subset which is called 2, 3, and so on. You can take any two elements and form subsets. And surprisingly, you can even take 1 to 3 and call it a subset of A. And that is, even though it's a subset, it's not a proper subset. So these guys are proper subsets. However, as the last piece, when you write 1, 2, 3, this guy is not a proper subset. However, we just want subsets. We don't put much emphasis on proper or improper right now. So now if you count how many subsets are there, you will find there are 8 subsets. Why? Because 1, 2, 3, 4, 5, 6, 7, 8. Yeah. And if you take all of these subsets and put them in another set like this, um, let's call it, I think the notation goes something like this, P of A, you know, obviously that will be the power set. That's why I'm using the word P. And P indicates that, P of A indicates that it's the power set of A. That means it's coming out of A, generating out of A. So if you put all of these guys into another set, 1, 2, 1, 3, 2, 3, and finally I guess 1, 2, 3. Yeah. This set is called a power set. So the definition of the power set is the collection or the union of all possible subsets of a set. That's all that that's all that a power set is. And you can even try out for more numbers and just play around with it. Maybe you take B as 1, 11, 2, -9. You have four elements right now. And if you do it what I did over here, you will see that there are 16 subsets. And in general, if your set has n elements, let's say it has 1, 2, 3, da 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 da, or let's not use 1, 2, 3, let's say A, B, C, da 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 da. Like n, some sort of, there are n number of elements. In this case, the subset will be 2 over n. You can do it, you can try to prove it by induction, and I'm pretty sure the proof exists in Wikipedia and whatnot. Like you can just Google it up and see why this is the case. It's a combinatorial problem, that's all. So this is all we had to say about Venn diagrams, and I realized that I missed mentioning about power sets and proper subsets and improper subsets. So that's why I tried to cover today. So if you think this content is helpful to you at any way, sort of form, let me know. And yeah, consider supporting us through subscribing. Thank you.